In this lecture, we discuss about equilibrium points, stable equilibrium, unstable equilibrium, and all the previous questions. Okay, so this lecture is entirely about stability analysis. So, as a fundamental, you have to know some idea of a slope. Okay, then I can develop some logical ideas, so you can easily use this concept to identify these problems, identify these stable and unstable equilibrium conditions. Okay, so what is the slope? So when graphically I will discuss this concept. So this is a coordinate system. Here it is a coordinate is x, and this is v of x. Okay, and if this is a variation of, so as x increases, v of x varies like this. Okay, here what is the slope? That means if these are the two positions, x1, and this is another position, x2. Now what is the slope? So to find out the slope, I have to extend this point, and I have to extend this point, and extend this coordinates to this points to v of x coordinate. Okay, like this. So here I get a triangle, and in this triangle this length is equal to delta v, and this length is equal to delta x. Then slope is defined as equal to delta v by delta x. That is, slope means how much of v is varying with respect to x. So here you get this delta v. Delta v means this is the v2, this is v1, and this is v2. That is v2 minus v1. That is, this is the final position, this is the initial position. So final position minus initial, that is v2 minus v1 by x2 minus x1. So v2 is greater than v1 and x2 is greater than x1. So this is positive. Here this slope is positive. Now I am taking another point, another condition. Here this is the variation of v of x with respect to x. That is, v of x is constant with respect to x. So what is the slope here? So here the slope is delta v by delta x. And what is the delta v? Here you can see there is a delta x when we are considering this x1 and x2. Here there is x1 and x2. So there is a delta x. And there is no delta y. That is, delta y equal to 0. So this is 0 by delta x. That is final position minus initial position. That is x2 minus x1. So x2 is positive, x2 is bigger than x1. So this is, anyway, this is equal to 0. No need of these things. Okay. Now another condition. Now v of x is varying like this. Okay. So now taking these points, these are the x1 and x2 positions. So here delta x is this one, x, and delta y is this one. Now what is the slope here? That is delta v by delta x. That is equal to the final minus initial. So final v is this one. Okay, this is the v final v, and this is the initial v. Okay, v initial. Here vf minus vi by xf minus xf minus xi. That is vf is less than vi. So and xf is greater than xi. So this quantity will be less than 0, is equal to negative quantity. That is, this will be, so this quantity will be, slope will be negative, and here slope is 0, and here slope is positive. Okay. So for a positive slope, v of x is increasing with respect to x. So this have positive slope. And here v of x is not changing with respect to, it is not increasing or it is not decreasing with respect to x. So slope is 0. And here v of x is decreasing with respect to increasing x. So slope is negative. So these ideas will help you to understand this idea of stable and unstable equilibrium conditions. Now we are considering a case, a graph. So another graph. This coordinate is v of x, and this coordinate is x coordinate. And now here the function is varying like this. Okay, this function is varying like this. Now it is a example of a hill like that. Okay, so now suppose this is a hill, and if you are placing a ball here, okay, what will happen? It can stay there if you put it exactly at that point, that peak point. And okay, and if you slightly touch on that ball, it will go down in this direction, or it will go down in this direction. So this ball can stay or can stay at that peak position, but if you give some force or something, it will go somewhere else. So this is some kind of equilibrium, and this equilibrium is called the unstable equilibrium. Now you are placing this ball here, okay, and you are moving this ball to here, giving a force, so this ball will move to here. After some time, and if you take your hand from this ball, what happen? It will come back and it will oscillate, and finally it will settle down at the position. This is the, okay, this is the this, we can call these are the local minima and the local maximum. Local minima, and this local minima, it will come and rest. It's local maxima. So the local maxima and local minima are the some kind of equilibrium points, and here you can see this will come to rest after some time. So we can say it is a stable equilibrium point. Okay, So now we are going to make a mathematical idea of this concept. Okay. So what is mathematically stable equilibrium? That is what we are going to do. So equilibrium point. How we can find out equilibrium point if a function is given. So here you see these are the unstable equilibrium point and stable equilibrium point. And if you take slope of this equilibrium point, stable equilibrium point, it will be parallel to x-axis. And if you take the point of unstable equilibrium, the slope will be parallel to axis. So one of the condition for equilibrium point is at equilibrium point, slope is equal to 0. So to find out equilibrium point in a equation, you just find out the slope. Okay, if slope is 0, that point will be, that point correspond to that slope will be an equilibrium point. Okay. So how we represent a slope in a mathematical way? That is dy by dx. Okay, that is here dv by dx, where v is a function of x. And if dv by dx equal to 0, then it will be an equilibrium point. Okay. So here a slope at this position, that is x1, and at this position x2, both have a 0 slope. So here x1 is a equilibrium point and x2 is a equilibrium point. But we don't know whether these are stable equilibrium or which one, x1 or x2. So in this graph we know x1 is a unstable equilibrium point and x2 is a stable equilibrium point. So here we know mathematically this is a equilibrium point. Now we have to find out whether which one is stable and which one is unstable. So we need mathematical expression for stability analysis. Expression for stability. That is what we are going to find out. Okay. Here you see this is a unstable equilibrium point, and if you are moving from this equilibrium point, unstable equilibrium point, to somewhere, then the slope will be like this. So it is going downwards. Okay, and if you are moving from a stable equilibrium point to the positive x direction, the slope will be positive. So here the slope is positive and here the slope is negative. So we got another condition that variation of slope, that is the variation of slope with respect to x is negative, then it will be unstable equilibrium, and variation of slope is positive, then it is a stable equilibrium point. That is, we can express mathematically like this one, that is d by dx of slope is negative less than 0, then it will be unstable equilibrium point. And here we know what is slope. Slope is dv by dx. So in pure mathematical form, d square by dx square of v of x equal to is, if it is less than 0, then it will be unstable equilibrium. Now we have to find out the condition for stable equilibrium. So d by dx of slope, if it is greater than 0, okay, so in this graph you can see here the slope is positive slope, so variation of slope with respect to position is positive. So this is the condition, then it will be a stable equilibrium point. That means d square of vx by dx square, if it is greater than 0, then it will be a stable equilibrium point. Okay, so we find out the mathematical expression for stable and the unstable equilibrium points. And here I tell some examples. One is simple pendulum. Okay, simple pendulum is like this one. It is attached to a support and there is a bob of mass m and it is oscillating like this. Okay, and for this simple pendulum, if you give some force to this pendulum, it will oscillate and after some time it comes to rest, and that point is called the mean position, and this mean position is a equilibrium point. And you can see after some time, if it is displaced from its equilibrium point, after some time, after some oscillations, it will come and rest at its equilibrium point. So the oscillation is about its equilibrium point. Okay, oscillation is about equilibrium point. Equilibrium point. Now we consider another example, that is a simple harmonic oscillator. So this is a simple harmonic oscillator. This is a spring of constant K and there is a mass M. So this mass will oscillate about a mean position, and this mean position is a equilibrium point. Okay, so if we move the mass to positive direction or negative direction, after some time, after some oscillation, it will come and rest at its mean position, that is the equilibrium point. So here also oscillation is about equilibrium point. Why I am telling this concept is there is a set question related to this concept. This one is a previous CSIR problem and it is a part B problem. Here they given a potential, that is V of x equal to a x square plus b by x square, where a and b are the constants, and they are asked to find out the angular frequency omega of small oscillation about a minimum potential. That is, if you are plotting this V of x versus x, the graph will be something like this one. Here you can see this point is a minimum potential point and the oscillation is about this point, right? So the corresponding point is x, and how we can find out this x value? We know for this point the slope will be equal to 0. That is, slope will be equal to 0 for that particular point. That means dou v by dou x equal to 0. So if we are taking derivative of potential with respect to x and equating to 0, we can find out this x point. So that is I am going to do, that is dou v of x by dou x, that is equal to 2ax minus 2b by x cube, and I am equating this value to 0. And here I am multiplying this whole term with the x cube. So I get 2a x raised to 4 minus 2b equal to 0. Here I can cancel this 2 and 2. So what I get x equal to b by a all raised to 1 by 4. So this is the point, equilibrium point. Now I am introducing some ideas about small oscillation. You know SHO. For SHO, the equation of motion is x double dot equal to minus omega square x, where this omega square is nothing but k by m. That is omega equal to root k by m. And what is this k? This k value is equal to dou square v by dou x square at equilibrium point. I will discuss these ideas when I am discussing more about small oscillation. Okay, don't worry. Right now you just remember this equation. Okay. And here they are asked to find out the omega of a unit mass. That is here m equal to 1. Therefore we get omega equal to root k. Therefore this omega here is equal to root dou square v by dou x square at a equilibrium point. Now we have to evaluate dou square v by dou x square, and we know the equilibrium point. Equilibrium point is x equal to b by a all raised to 1 by 4. So first we have to find out dou square v by dou x square. Earlier we got dou v by dou x equal to 2ax minus 2b by x cube. So what will be the dou square v by dou x square? This will be equal to 2a plus 6b by x raised to 4. Now we have to substitute this x value. So what we get? It is equal to 2a plus 6b by x raised to 4. Here x equal to b by a all raised to 1 by 4 raised to 4, that is b by a. So we can cancel this b and the b. So what we get? We get 2a plus 6a, that is equal to 8a. So we got the dou square v by dou x square value. Now substitute this value here. So what we get? We get omega equal to root 8a. So this is the answer. This is a 2017 set question, and the question is, the oscillation of a point mass could occur about a point of dash equilibrium. The options are unstable, stable, neutral, and both A and B. So just before I discussed, the oscillation will occur about stable equilibrium point. So this is the right answer. Here this one is another CSIR problem, and it is also a part B problem. And here in this problem they given a potential, that is V of R equal to minus A R raised to minus 6 plus B R raised to minus 12. And they asked to find out value of potential at a equilibrium. We now at equilibrium, the dou V by dou R will be equal to 0. That is, slope will be equal to 0. So by using this condition we can find out the value of R. Then what is dou V of R by dou R? It is equal to 6A R raised to minus 7 minus 12B R raised to minus 13. And we are equating this to 0. So 6A minus 12B R raised to minus 6 equal to 0. That is, R raised to 6 equal to 2B by A. So we get R equal to 2B by A all raised to 1 by 6. Right. Now we got the value of equilibrium point, that is R equal to 2B by A all raised to 1 by 6. Now we have to substitute this value in our potential, that is V of R equal to minus A by R raised to 6 plus B by R raised to 12. Now you substitute this value of R in this equation and you will get the answer. Write the answer here. Okay, it is simple. You just do it by yourself. Okay. This is a 2018 June question. Okay, the question is, a particle is placed in a potential given by V of x equal to half kx square minus 1 by 4 gx raised to 4, where k and g are positive constants with g less than k. Then x equal to 0 is a point of stable equilibrium, x equal to root k by g, and x equal to minus root k by g. These are the point of stable equilibrium, etc, etc, etc. Okay, so what we want to find out here is, we have to find out what are the point of equilibrium. First we have to find out equilibrium point, then we have to find out which equilibrium point is stable and which equilibrium point is unstable. Okay, so that is what you have to do. So here what is given is potential V of x, and V of x equal to 1 by 2 k x square minus 1 by 4 g x raised to 4. First what we want to find out is equilibrium point. So first we want to find out equilibrium point. The condition for equilibrium point is slope equal to 0. That is, dv of x by dx will be equal to 0 at the equilibrium point. Okay, so here v of x is given, so we have to take derivative of this function with respect to x. So what we get is kx minus gx cube. Okay, this is equal to 0. So the equilibrium points are, we can take the common term, that is x into k minus g x square equal to 0. Here one important point is, you do not take, never take k x equal to g x cube and cancel this one of the x and cancel one of x here and writing k equal to gx. If you do in this way, then your answers will be pakka wrong. Okay, so don't do this kind of work. Please follow this method. So if there is a common x term is there, take it out and include the other terms inside this bracket. So here this function can be 0 with the two conditions, that is maybe x equal to 0. So one equilibrium point is x may be equal to 0. So this function can be equal to 0. And second possibility for this function to be 0 is k minus gx square equal to 0. Equal to 0. That is equal to x square equal to k by g and x equal to plus or minus root k by g. So these two are the equilibrium points. X equal to 0 is the one of the equilibrium point and x equal to plus or minus root k by g is the another equilibrium point. So we got equilibrium points. So now and the equilibrium points are x equal to 0 and x equal to plus or minus root k by g. Now we want to find out which one is stable equilibrium point and which one is unstable equilibrium point. So we are going to do stability analysis. So what is the condition for stable and the unstable equilibrium point? That is change in slope d by dx of slope. If this is positive greater than 0, then it will be stable equilibrium point, and if it is less than 0, then it is a unstable equilibrium point. Okay, so what we have to evaluate is d by dx of this function, that is slope is dy by dx, and we already find out, sorry, dv by dx we already find out, that is this one, dv by dx, that is kx minus gx cube, kx minus gx cube. So this is equal to k minus 3g x square. So this is the function, that is d square v of x by d x square equal to this function, that is k minus 3g x square, k minus 3g x square. Now we have to evaluate this function at equilibrium points. Okay, okay, now we have to evaluate the value of d square v by dx square at the equilibrium points. So first equilibrium point is x equal to 0. So substituting x equal to 0 in this equation, that is k minus 3g x square, then we get then what we get? So x equal to 0, we get k. This is greater than 0. Okay. That means x equal to 0 is a stable equilibrium. Now we have to check the second equilibrium point. Second equilibrium point is x equal to plus or minus root k by g. Now substitute this value in k minus 3g x square. So what we get? K minus 3g into x square is equal to k by g. So this g by g will cancel and we get minus 2k, which is less than 0. If d square v of x by dx is less than 0, this will be unstable equilibrium. Okay. Now you can go back to your question and you can answer. So now check the options. X is equal to 0 is a stable point. We've seen that x equal to 0 is a point of stable equilibrium. And option B is x equal to root k by g and x equal to minus k by g. These are the points of equilibrium, but these are not the points of equilibrium. Okay, points of equilibrium are x equal to root k by g and x equal to 0. And you get these options when I told you in between the lecture you have to follow some method. So you have to take the common x term outside and you have to equate to 0. So if you didn't done that thing, if you cancelled out this x on LHS and RHS, then you get these options. Okay, so these options are not correct. These equilibrium points are not correct. The correct equilibrium points are what we obtain now. Okay, so here this is the answer. Option A is the answer. This one is another CSIR problem and it is a part C problem. Wow, 5 marks problem. But it is simple. You see, here they specify the potential, that is V of x equal to 1 by 4 into x square minus 2 all square, right? And it is a double well potential. And what is the question? The question is we have to find out the angular frequency omega. It is given omega equal to root 2 and omega equal to 2. And the third option is particle will switch between right and left walls, and option D, the particle will approach the bottom of right well and settle there. Here, which of the options have much similarity? Here you see omega equal to root 2, omega equal to 2. So among these 4 options, these 2 are much more similarity, right? So I am predicting that these C and D will not be the options. Why? Because the questionnaire knows you do this problem to some extent, but at the end, at the last step, you will make some mistakes and you will land on the exactly wrong answer. You see, the difference between these two are 2 and root 2. So there is a chance for mistakes. That is why that guy is giving similar options. So my prediction is this one, the option C will not be the correct option and option D also will not be the correct option. The correct option will be one among A or B. Maybe you have some doubts. Okay, don't worry. We are going to solve this problem exactly. Then we can come back to the options. In this problem, the given potential is V of x equal to 1 by 4 x square minus 2 all square. First, I am going to solve this problem by graphically. So first I am going to draw the diagram of this potential. Therefore, I am taking my axis, that is x and y. X and V of x. Okay, now I want to plot this function. Right now I am not considering this term, that is 1 by 4. Right now I am taking v of x equal to x square minus 2 all square. I am neglecting the 1 by 4 term because just to simplify the problem. Here I am going to plot this function v of x equal to x square minus 2 all square. So if I am removing this 1 by 4 terms, the shape of the graph will not change. What I want is, I just want to know how this potential varies with respect to x. Okay, so here I am taking x equal to 0. The corresponding potential v of 0 will be equal to, substitute this value of 0 here, so you get it is equal to 4. So that is this point. When x equal to 0, v will be equal to 4. Now I am taking the another point, that is x equal to plus or minus 1. Then what will be the v of plus or minus 1? It will be equal to 1, right? That is, for x equal to plus 1, the value is 1, and x equal to minus 1, the value is 1. And another point, when x equal to plus or minus 2, the v of plus or minus 2 will be equal to 4, right? That is these points. Now I got the shape of this potential. It will be like this one. The exact shape is little different, but this is sufficient for me because I just interested in its shape only. In the question itself, they are specifying the particle is moving infinitesimally from the minimum of the potential. So the particle may be at this position or the particle may be here. So there is a infinitesimal displacement. Now itself you can exclude two options. See, option C is the particle will switch between right and left wells. This is the right well, right? And this is left well. Here you can see in between there is a high potential. So for an infinitesimal displacement, this particle can go to the another well. So option C is wrong. It will not switch between left and right wells. So C is wrong. Now what is option D? The particle will approach the bottom of right well and settle there. That condition is possible if the potential is like this one or something. So if this is the potential, then if the particle is here and if we are slightly displacing this one, then it will reach in the second well. But here the potential is not like that. Okay, so option D is also wrong. Now you see, you excluded two options. Now you definitely know one among the other two, that is A or B is the correct answer. So even if you choose A or B randomly, then also the probability of getting mark is 50%. Right? This is very interesting thing because the total mark of CSIR exam is 200 and its 50% is 100 marks, and that mark is sufficient to qualify NET or JRF most of the time. Okay, so your probability of qualifying the exam is now 50%. If you can exclude two options among four, then your probability of qualifying the exam is more. Here you see, I didn't done anything, right? I didn't know any theory. I didn't told you any theory. What I told you is just basic things, very basic things. I drawn one graph, and drawing graph is 10th class thing. And to understand this idea, that is particle will not or ball will not switch between this kind of two wells, that is also you know from your daily life. So even you don't know anything, any higher level physics, and just by knowing 10th class, 12th class subject, you can you have a probability of qualifying the CSIR exam. That is 50% probability of qualifying the CSIR exam. Okay. And the option A and B are about angular frequency. And I already told you angular frequency omega equal to root k by m. And this is equal to root dou square v by dou x square by m, where we have to evaluate this dou square v by dou x square at equilibrium. And at which equilibrium? At a stable equilibrium. Why? Because then only it will execute periodic oscillations, right? Now we have to find out what are the stable equilibrium points. Now we have the figure. So which one will be the stable equilibrium point? You know, this will be definitely unstable. Why? If you placing a ball here and if you slightly displacing it, it will fall down and it will not come back to its initial position. And you know, these two are stable equilibrium points. Why? If you're displacing this particle slightly, it will come back to its initial position, right? So if the particle is at this position, it will not execute SHO. So there will not be any periodic motion. And if the particle is in a stable position, this or this one, then it can execute oscillations. And if you consider this 1 by 4 times, then the reference axis will pass through this one. Then this will be the reference line. Now you can see the potential V of x is 0 when it is at a stable equilibrium points. So at which value of x, that is we have to find out this x value and this x value. So how we can find out this x value? We know V of x at this position is 0 and we know V of x equal to 1 by 4 into x square minus 2 whole square. Therefore, if we substitute the value of root 2, that is x equal to plus or minus root 2 in this equation, we get V of x equal to 0. So these two are the x value corresponding to stable equilibrium point, minus 2 and plus 2. So we got the value, stable equilibrium point value, that is plus or minus root 2. That value we have to substitute in dou square v by dou x square. And here we know V of x equal to 1 by 4 into x square minus 2 whole square. Then what will be the dou v by dou x? It will be equal to 1 by 4 into 2 into x square minus 2 into 2x. So this 2 and this 4 will cancels. The remaining what we get is x cube minus 2x. So taking the one more derivation, that is dou square v by dou x square, but we get 3x square minus 2. Now substitute the stable equilibrium point value, that is x equal to plus or minus root 2. Then what we get? It is equal to 3 into root 2 whole square minus 2. That is 6 minus 2 equal to 4. So what is omega? Omega is equal to root dou square v by dou x square, that is 4 by m. And in this problem, m is taken as unit mass. Then we get omega equal to 2. Now check which one is the correct answer. Option B. This is a 2017 June set question. Okay. The question is similar to what we discussed just before. The question is, a particle is placed in a region where the potential is V of x equal to half k x square plus 1 by 3 lambda x cube, where k is greater than 0 and lambda is greater than So here also what we have to find out is what are the points of state equilibrium, and which one is the unstable equilibrium, which one is the stable equilibrium, that kind of thing. Okay, so for such a problem, the starting point is potential, the function, that is v of x equal to half k x square plus 1 by 3 lambda x cube. Now the next step is finding the equilibrium points. Okay, and we know condition to find out equilibrium point is slope equal to 0. That means dv of x by dx equal to 0. Now we have to find d by dx of this function. Okay, so d by dx of this function will be equal to d of x by dx will be equal to kx plus lambda x square, and this will be equal to 0. So we take the common term, okay, that is x into k plus lambda x equal to 0. Now this total function equal to 0 when x equal to 0 or k plus lambda x equal to 0. That means the x equal to minus k by lambda. So these two are the equilibrium points. One is x equal to minus k by lambda and another is x equal to 0. Now we have to find out the stability of this equilibrium point. We have to find out which point is stable equilibrium and which point is unstable equilibrium. So stability analysis. So the stability analysis, we know d by dx of dv of x by dx. If this quantity is greater than 0, that is positive change of slope, then it will be a stable equilibrium. And if it is negative, then it is a unstable equilibrium. So we have to find out d by dx of dvx of dx. Okay. Here we know dv by dx equal to kx plus lambda x square. So we have to take one more derivative with respect to x. So what we get is this equal to k plus 2 lambda x, that is d by dx of dv of x by dx, or d square v by d x square equal to k plus 2 lambda x. So now we have to find out d square v by dx square at the equilibrium points. Okay, so what are the equilibrium points? One is x equal to 0 and another is x equal to minus k by lambda. Okay. Now we substitute this value in k plus 2 lambda x. So x equal to 0. So what we get is this is equal to k. K is greater than 0. So as per this condition, it is a stable point. That is, x equal to 0 is a stable equilibrium point. Now we have to substitute this value of x in k plus 2 lambda x. So what we get here, k plus 2 lambda into minus k by lambda. So this lambda will cancels and we get is equal to minus k. So here this is minus k, that is less than 0. That means x equal to minus k by lambda is a unstable equilibrium point. So now we can check the options given. Among the options, the option C is the right answer. So x is a point of stable equilibrium and x equal to minus k by lambda is a point of unstable equilibrium. But you don't want to do all these things to solve this problem. Then why I told you these things? I told you these things only to get insight into the problem. Now you know the problem more conceptually, not just some mathematical equations, right? Now I am going to tell you the exact procedure to solve this kind of problems. So you don't want to think about what will be the diagrams, what will be the graph, what will be the potential looks like. Don't worry, you just follow the exact step. It is purely mathematical steps, and if you didn't made any mistakes in between solving this problem mathematically, you will get full marks. Here I am not discussing much physics, I am just using the mathematics. Okay, see, the first step in this procedure is you have to write down the potential, the given potential in the problem. Second step is you take derivative dou v of x by dou x of this function and you equate that value to the 0. Then you can find out the x values, maybe 1 or 2 value will be there. The third step, you have to take derivative of this function once again, that is dou square v by dou x square, and you substitute these values, x values 1 and 2. So maybe you get this one greater than 0 or this one less than 0. Greater than 0 means the change of the slope is positive. That means the particle is here. This is my x-axis, see? And if particle is slightly moving in this positive x direction, the slope will be in the positive direction. Okay, so you can easily figure out if particle is moving like this, then it will definitely come back to its initial position. Then it will execute simple harmonic oscillation. So there will be a frequency, and you know omega equal to root k by m, and you know this is equal to root dou square v by dou x square by m. This m is in the inside the root, and you have to substitute the value